An electric dipole consists of two charges of equal magnitude and opposite sign separated by a distance 2a as shown on the next slide. The dipole is along the x-axis and is centered at the origin. If the electric potential is taken to be zero at infinity, calculate the electric potential at any point y on the y-axis. Calculate the electric potential at any point x on the x-axis in between the two charges. And if one charge q is 4 microcoulombs and a is 2 centimeters, how much work is required to bring a third point charge of minus 4 microcoulombs from infinity to the point at 1 centimeters on the x-axis? Let's start with our own sketch of this scenario. We have an x and a y-axis. Located at the position of minus a, we have a positive charge. And located at the position of positive a, we have the negative charge. We want to find the electric potential at any point on the y-axis, and specifically on the positive y-axis. So let's pick an arbitrary point right here on the positive y-axis. Let's just call the value of y at this point b. Remember, surrounding every charge in space is an electric field. This electric field is a conservative vector field, and therefore, in the presence of another charge, gives that other charge the ability to store energy in the form of electric potential energy. In the absence of a second charge, like at this point B, the electric field still has the ability to give another charge, if we were to place it at point B, a potential energy. But in the absence of that second charge, the measure of the electric field's ability to give that energy is called electric potential. Remember, electric potential due to a point charge, Q, is directly proportional to that charge divided by the distance the point is away from that charge. Point B is a distance r away from our positive charge. Let's label our positive charge Q. Let's label our negative charge minus Q. Because Q and minus Q are symmetric about the y-axis, our negative charge in our dipole is also the same distance away from the point B on the y-axis. And remember, point B can be any point on the y-axis. So in order to find the potential at point B, we could apply superposition. Electric potential follows the superposition principle, which says the total electric potential at a point is equal to the sum of the electric potentials contributed by a number of different particles. In this case, we have two particles. We have a positive Q and we have a negative Q. Each of these particles will contribute to the electric potential at point B. So for the electric potential for the positive charge, we know that is kq over r. The electric potential for the negative charge is equal to minus kq over r. When we sum these two potentials, the potential of the positive charge and the electric potential of the negative charge, the sum is 0. this means that the electric potential at any point on the y-axis is equal to 0. That makes sense because positive charges are sources of positive potential. Negative charges are sources of negative potential. These two charges in this dipole have equal magnitude and opposite sign, and they're equally distant from the same point. This means that any point on the y-axis has a value of 0 potential. And what that means is if you were to place another charge at any point on the y-axis, it would have 0 electric potential energy due to this dipole. Let's look at a couple of equipotential lines for the positive charge. Remember, equipotential surfaces surround point charges as concentric spheres about the point charge. So I'm just doing a couple of equipotential surfaces for each of these point charges in our dipole. Let's say the potential for this inner surface around charge Q is V1, and for the outer surface is V2. And remember, for positive charges, potential decreases with distance. Now, for negative charges, potential increases with distance. So for surrounding the negative charge, I will just put this as minus V1 and this is minus V2, where in this situation, minus V1 is less than minus V2. Now that makes sense because the larger the magnitude of a negative number, the smaller its value. Here then, you could see that at point B, the total electric potential is the sum of these two electric potentials due to the positive point charge and the negative point charge. Since it's the sum of two potentials that have the same magnitude but opposite in sign, it makes sense that any point on the y-axis that is right in the middle, equidistant from both of our source charges, will have a total value of 0 potential at that point.